I've recently created a few slime mold simulations, and that's what I want to talk about. But first I need to put my degree to some use and talk about life a bit. I'll be going off on a bit of a tangent now. Bear with me. So what is the goal of any successful organism? Well, it's to survive and thrive, but what does it mean to actually survive and or thrive? Surviving means that we're actually being alive. That might sound trivial, but it does come with a few problems. First of all, it's actually not that easy to define what it means to be actually alive. But we can identify a few properties that are required but not sufficient to be classified as being actually alive. Let me give an example. For example, most organisms, we would agree, have the ability to interact with the environment of some way. Like a fish can swim, bacteria can split apart and grow and consume food. And I think we would all agree that even though a computer, like a drone, can navigate the environment, interact with it, even self-charge to some degree, consuming food, we would not call that as being alive, even though it has some of the properties that living things have. So let's return back to the actual properties, or some of the properties that are required to be alive. The first one would be to react to stimuli, the environment. It needs to interact with something to some degree. And usually we also say it has the ability to move and can grow and reproduce in some way. One thing we can observe with most of these properties is that they all require energy. You cannot move without consuming energy. You can certainly not grow and reproduce without consuming energy. And as such, any organism will need to balance its energy intake versus its energy consumption. Simply for the matter that an organism that consumes more energy than it takes in will sooner or later just run out of energy and die. But that also means that any living thing will need to continuously consume food. And from that we can derive a few actually contradictory goals. We need to be constantly on the search for food, and we want to optimize or reduce the amount of energy we're actually consuming for whatever it is that we're doing. Why is that contradictory? Well, the act of looking for food actually consumes energy, because we'll need to to explore the environment, we'll need to probably move to the food source. If you look at humans, just chewing takes energy. So if you eat something that gives you less energy than the act of chewing it consumes, you don't really need to eat that thing. And the simulation I wrote explores how the slime mold, or Physarum, is trying to achieve those goals, or well, a simplification of it. Why is the mold that interesting? That is because the slime mold is actually not a multicellular organism. Or rather, it has no nerves, it has no vascular system, no organs whatsoever. It's just a collection of cells that can move independently from each other and that somehow cooperate in a way that allows it to explore its environment in a quite complex way and build optimized transport networks for nutrients within it, again, without the ability to communicate between cells in a long distance. A cell can't only talk with its neighboring cell, basically. And it seems to achieve this with just a single chemoattractant or pheromone that it deposits on the surface it's living on, and the cells just read them. And that's also how the simulation works. So the way the simulation works is that it's a bunch of agents, cells, that are living on a plane. In this case, a 2D world, which is circular, but it doesn't matter. And they're all moving about the plane. The simulation is divided in a few steps. There's a pheromone deposition and diffusion step, and a actual movement step. Let's talk about the movement step first. Every agent will pick its direction to travel in based on the gradient of the pheromone that it can observe. It has, so every cell has a sensor in front of it and one to each side. And it'll sample these points, and based on the concentration of the pheromones in those points, it will choose a direction. If it cannot find a meaningful gradient, it will pick a random direction. And in my case, there's a slight bias to the right side in that. I will come to that later. And after it's done moving, it's going to deposit a small amount of the attractant, the pheromone, on the plane. Then in a second step, the pheromones will diffuse across the plane, so they'll spread out, and also evaporate, so that we don't oversaturate the plane. This has two consequences. Firstly, it achieves the goal of optimization, actually, this step. Because if we imagine that we have a curved path of pheromones, then diffusion will actually straight this path out naturally, without any interaction from us. And evaporation will invalidate no longer used paths, so that less cells travel along them. The concept of exploration, on the other hand, is handled by cells hitting the edge of the network and then picking a random direction to travel in because there's no gradient to follow. And the right-hand bias that I just mentioned, in my case, is there to improve cohesion. So I'm not quite following the paper. My cells do not have cell collision, which the paper has, and I'm sure that changes the behavior quite a bit. But this is my first project on the GPU, and I'm not quite comfortable with it yet, and it's a lot more complicated, and I don't want to go into it right now. But suffice it to say, I chose to not use cell collision, which means that my cells can actually collapse to a point, which they can't do in the paper. And my cells also spread out more. I don't know if the original algorithm has the same issue. I would say it does, looking at it. I don't see how cell collision prevents it, but basically the network disintegrates into many smaller groups because there's nothing holding, there's no attracting force inside the network. Once it leaves the actual influence of the gradient. And any cell that leaves the network will also travel in a straight path because there's no gradient left to follow. So by introducing the right-hand bias in my case, I make the cells all drift to one side, which has the effect that on the outside of the network, these cells will travel along the path, capturing more rogue cells and improving cohesion, while also, when it's exploring, not traveling in a straight line, but covering more of a distance by curving rightwards. You can see that in the simulation. And I found this as a much better result than without the bias. The simulation also has a pre-pattern in the world, which is sources of what we could consider food, but they are biasing, but it biases the network towards those points, and that's the 3 dots you see in the simulation. And the original paper will be linked in the Discord. A link to my source code will be in the Discord. It's a Rust project. And if you've got any questions, I have a Discord, or leave a comment. If you like my content, like and subscribe, and have a good day.